Okay, today we look at lecture number 6, unit number. So we are talking about the circuit basic circuit concepts, in which we talked about sheet resistance. Okay, so in the last class we have seen what is the sheet resistance we have calculated. The resistance from A to B of any material is defined by rho L by A. If length is equal to width, area becomes square. Area becomes square area. Okay. So in that sense, whatever the resistance RAB is there, we call it as sheet resistance RS, which is defined by rho by T. That is what we have defined. So the sheet resistance does not depending upon the size of the square. It's only depending upon the thickness of the material and the resistivity of the material. And its units are ohm per square. Ohm per square. That is what we have calculated. Okay. And once again, we have already seen what is the sheet resistance for each and every material at different technologies. So what is the values that we have seen? Let me recall again the things. So because it's important to calculate something, so I want to copy those things again. If we take a different layers, okay, so whatever the essential layers that we have seen, if we consider those things, these values are shown in this way. Okay. So these are the different technologies we have taken into consideration. One is 5 micron technology, orbit to 2 micron technology. This is a 2 micron technology, 0.12 micron technology. So what did this 5 micron says that whatever the transistor, whatever the devices that we are using in a particular chip, the feature size is 5 microns. It may be length. It actually decides the length of the transistor. Okay, so therefore the feature size is also becomes minimum of 5 microns we have to maintain. Okay, so in that particular thing, we consider we are using the metal, we are using the diffusion, we are using the silicides, polysilicon, and N channel, P channel. So as I mentioned that it's a polysilicon with metal is called silicide. Okay, polysilicon with metal is called silicide. So this is mainly used to reduce the polysilicon sheet resistance. So actually polysilicon sheet resistance is this much at 5 micron. So it is reduces from 2 to 4 because of metal is introduced with the polysilicon. Anyway. So now whenever we have any material you consider, for example, you take a metal here, for example, this is the metal. Okay. So if you want to consider what is the resistance offered by this metal, what is the resistance offered by this metal or metal, for example, is defined in terms of its size with sheet resistance. So in terms of its size with sheet resistance. Okay. So therefore the sheet resistance of a material we know, and what are the dimensions of that thing is there. that we can define. Or in terms of, or we can say that we have to divide the entire material into different type of squares. How many number of squares are there? Okay, so for example, this is one square, second square, third, fourth, like this. How many number of squares are there? For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore, it will be 9 RS will be there. So in RS, we can substitute that value, we will get that one. Okay. So this is for a material point of view. For example, if I want to calculate the resistance of a circuit, let us consider a circuit. Okay, a simple. Let us calculate. So calculate the on resistance of the on resistance NMOS inverter. On resistance of an NMOS inverter. Okay, so what is the NMOS inverter? As we know that we have a depletion mode type of transistor. Okay, we have a depletion mode type of transistor. The thickness is must be good. We have to show in this way. This is a symbolic diagram, and this is an enhancement at the bottom. Right, this is connected to VDD. This is connected to ground, and the gate is connected to the source of this type. So this is called VN. This is called VOut. Very important to note that. So what is the dimensions of the physical dimensions of this NMOS transistor in terms of the lambda based design rules? So length to width ratio we should tell. So what is the length to width ratio of this particular transistor? So here it's very important to note that 2 lambda into is to 2 lambda that we have to consider. Length is 2 lambda in terms of the lambda based design rules. 2 lambda for length of the enhancement, 2 lambda for the width. Whereas the depletion type mode transistor is not like that. It is 8 lambda. The length of the depletion type mode transistor is 8 lambda, and it will be the same value that we are considering. It will be same thing that we have considered. Now, so this is what the dimensions of the device transistor, dimensions of the circuit I have given, and we need to calculate the on resistance. What do you mean by on resistance? Okay, the on resistance means whenever both the transistors are on, then whatever the resistance we can see from VDD to ground is called on resistance. Okay, when, so I'll write here, when both the transistors are on at any input voltage, is called on resistance. Is called on resistance. So that means you fix some particular voltage, input voltage. At that time, both the transistor must be on. Okay. So in this particular case, what input voltage will give you this kind of thing? So by VAN is equal to VDD, VN is equal to VDD. This is the point where both the transistor becomes on. That's what we have learned from the basic CMOS NMOS inverter. When the VN is equal to VDD, bottom transistor is on and upper transistor is always on. Therefore, the total circuit becomes on. Right? Now, under this situation, how do we calculate the resistance of each and everything? Both the transistors. Let us consider the resistance of this particular copy and paste here. Let us consider the resistance of this one is the resistance one is Rn. The resistance of this one is it's better to write it as R depletion, R enhancement. Okay. So the resistance of this particular transistor we talk about is the channel resistance only we need to consider. We need to consider channel resistance. Okay. So by the by, what is the resistance of this material and 10 years 70? What is its dimensions? Okay, what we are talking about, the RE is nothing but, it is nothing but length to width ratio is multiplied with RS. Length to width ratio is multiplied with RS. That is how we have to calculate. So that means that the sheet resistance value is multiplied with its dimensions. Its dimensions. Right? Therefore, what we can say that this is also called as, people will also called as Z into RS. So the dimensions of the transistor into the sheet resistance of that particular transistor. So the concept here is that what kind of sheet resistance I need to consider. Polysilicon I need to consider, or I need to consider diffusion I need to consider, or channel I need to consider. Which one RS I need to consider? Because metal is there, polysilicon is there, diffusion is there, channel is there, everything is there. But here, the sheet resistance of the channel we have to consider. What we have to consider? Sheet resistance of channel. Please remember that. The sheet resistance, because on resistance means once the channel is established, then only that will be on. As simple as that. So then only we have to calculate sheet resistance of this one. The sheet resistance of channel. Similarly, we have to calculate the RD is nothing but some Z value is multiplied with RS channel. Clear? Fine. Now, what is the value of this RS now? Here we can consider what is the Z here according to these dimensions. Channel dimension is 2 lambda by 2 lambda is the channel dimension. So this is what we can say. Therefore, 2 lambda divided by 2 lambda is multiplied with RS of the channel. So what is the RS of the channel? What is the RS of the channel that we have seen that? We are talking about the N channel. Okay. We are talking about the N channel. Let us consider 5 micron technology. Let us consider 5 micron technology. What is the value of this one? 10 to the power of 4 ohm per square. Okay. 10 to the power of 4. 10 to the power of 4 ohm per square. Or I can simply write it in this way also. Ohm per square. Ohm per square. Right? So therefore this value becomes 10 to the power of 4 ohm per square. So therefore this is what we consider that RE of this particular, the resistance offered by this particular channel, this particular transistor. Similarly, we calculate this one. What is the value that we can have? Z value is equal to 8 lambda by 2 lambda into RS. RS is, what is the RS of this? Is also N channel. Therefore, this is 10 to the power of 4 ohm per square, which is equal to RD. What is the value of this one now? So this value is equal to RD is nothing but 4 into 10 to the power of plus 4. 4 into 10 to the power of plus 4 square. Right? So this is what. So therefore now if I calculate the on resistance of this particular device, what is R on then? R on is simply both the devices are on. RD plus RN, RE, right? So therefore this becomes 5 into 10 to the power of 4 ohm per square. So this is how we need to calculate. Or you can say that simply sometimes we can call it as R on is equal to 50 kilo ohm per square. So can we write like this? Yeah, it is possible to write. So 50 kilo ohm per square will be the on resistance of a CMOS, sorry, NMOS inverter. Clear? Okay. Shall we write the on resistance of NMOS NOR gate? NAND gate is also simply we can find out. Okay. Let us consider on resistance of NMOS inverters. Okay. What we can do now? So on resistance of CMOS two input NMOS two input NMOS NOR gate. So by the by, actually we have considered only for we have previously we have only considered for the 5 micron technology assumed Rayala assume 5 micron technology. For example, if you use 1.2 micron technology, for example, if you use 1.2 micron technology, what is the n channel sheet resistance? 2 into 10 to the power of 4 per n channel. So therefore, if it is enhancement, the same value. If it is a depletion, 4 times it will be multiplied, and we have to add together. Okay, that means 4 times into 2 means 8 plus 2, 10. So 10 into 10 to the power of 4. That means 100 kilo ohms it will be. It will be 100 kilo ohms per square can be seen. Are you able to understand what I'm saying? So that's depending upon a technology that we are considering. So for the sake of simplicity, let us assume here is 1.2 micron technology. 1.2 micron technology. Okay, so what is the circuit diagram for this one now? This is the one. PMOS NMOS transistors. It is called VDD. This is connected here. That we call A, B. This is Y. Now, at what input voltage the transistors becomes on? So both VDD and so ground is also required. At what input voltages? Why did you use this specifically depletion transistor as a resistance part? No, actually, the thing is that we are talking about the on resistance of the transistor. So if the transistor is on means the channel is established there. Okay. So whenever the channel is there, then only we can say that the transistor is on. Okay. Therefore, the concentration here is that the channel formation. Okay. Therefore, we need to consider the channel resistance only. We need to consider. That's it. Okay. Is that okay? So now, what input voltage that becomes on? Okay, as we know that as we know that uh, except, or I can say that I can see for all other cases. or I can write it truth table also. For example, A, B, let us consider Y 0 0 0 1 1 0 1 1. So as we know that this is what the simple OR gate functionality, except this input is logic 0 0, except this logic 0. All other cases, the output is 1, logic 1. Okay. Or I can say that, for example, if here is 0, for example, this is the 1. We take 1 this condition. So therefore, this is becomes on, and this also becomes on. Possibilities here. Okay. The on resistance can be possible. Or otherwise, if it is 1, if it is 0. Okay. So this becomes off, but this becomes on. So here also on resistance is possible from P to depletion to NMOS. If it is 1 1, okay, there is a possibility of both the transistors are on. Okay, so there is exists a short circuit path between VDD to ground. Therefore, on resistance is possible, right? So we need to calculate for each and every case what is the on resistance of these three for the three combinations, right? So can you guess what is this? For example, in this case, let us consider R1. This is called R2. This is called R3. So let us consider R1 on. Let us consider this is R1 on. This is for the different cases. So let us calculate R1 on resistance anta. As we know that the previously we have calculated, okay, it is simply a NOT gate, right? So one is off, one is completely off, A is completely off, but B is available. So A does not affect the resistance of the B, okay? Therefore, simply I can write it R1 on is equal to 50 kilo ohms per watt per square. Agreed? So just it is a simple inverter, right? So that's what we can write. Similarly, R2 on is also here the B transistor is off, but the N transistor, A transistor is on. It's simply also inverter only. Okay. So therefore, what is the inverter R on resistance that we have seen earlier? Is also 50 kilo ohm per square. Right. So assume that, please remember that. So unless otherwise, if I not specify, you please remember that it's a length to width ratio is 2 lambda by 2 lambda. This is 2 lambda by 2 lambda. This is 2 lambda by 2 lambda. Okay. Or people will write sometimes. So it is also meaningful to write 1 is to 1, 1 is to 1, 1 is, sorry, 4 is to 1. It is also, we can write it like this also, 4 is to 1. Okay, in terms of lambda, each and every constant is multiplied with 2 lambda, because minimum feature size in this particular lambda based design rules is 2 lambda. We have to maintain the feature size. The width and lengths of the transistors are 2 lambda. That's the reason. Now, what about R on for this one? Okay, R3 on and as you can see here is that in this particular case, for example, the resistance R depletion. So this also offers some kind of resistance. Whenever it is on, some finite amount of resistance is there for a transistor. Simply the approximation is a resistance is formed there. Okay, so whenever it is on, it is also formed as a resistance. So this is what the structure is. This is what the structure is. So now what is the total resistance here observed? What is the total resistance? For example, this Rn1, this is Rn2. Okay. So the total resistance is Rd, and this is parallel combination, right? So Rn1 is parallel with Rn2. Okay. Therefore, total Rn is nothing but Rd plus parallel combination of Rn1, Rn2. right? So what is this value now? RD is actually 4 into 10 to the power of 4 that we know, plus what is the parallel value of NN1 and NN2? We know that 10 to the power of 4 into 10 to the power of 4 divided by 10 to the power of 4 plus 10 to the power of 4, right? Ohm per square. Can anybody tell me what is this value? 4 into 10 to the power of 4 plus 10 to the power of 4, let it be like this. It is 2 into 10 to the power of 4. Okay, so this will get cancelled. So now this becomes 2. Therefore, it is 2 into. Sorry, I'm extremely sorry. This is not possible.
Sir, it's plus, sir.
Yeah, it's plus.
Plus.
Okay, so this becomes 2. So it's 4 into 10 to the power of 4 plus 0.5 into 10 to the power of 4. Okay, so this is 4.5 into 10 to the power of 4 ohm per square. So in meaningful way that we can write it, what is the value? 10 cancel will get cancelled, 45, right? 45 ohm per square. So therefore this value R3 on is this value. So that means the resistance value is decreases. Now which on resistance we need to consider for this particular circuit? Okay, so all the time we have to give worst case values only. All the time we have to give worst case value. So worst case value if you give, then only it is possible to mention what is the operating condition of operating frequency of the device. Okay, so therefore to select which one is the on resistance of this device for worst case condition is 50 kilo ohm per second. Either 0 1 0 apply chesina 1 0 apply chesina with more resistance vastadi anamata than that of 1 1 apply chesinappudu. Okay, that's what we have to remember. So we have to take the worst case resistance values. Okay, now let us consider quickly. We have another 2 minutes or 3 minutes time is there. Please wait for another 2 minutes. We'll complete it. So let us consider on resistance of now. Let us consider on resistance of on resistance of uh, on resistance of CMOS inverter. CMOS inverter. So generally, under steady state condition only we need to calculate this one. Okay, what does it mean? Let us consider a PMOS transistor. Let us consider an NMOS transistor. When this both the transistors are on under steady state condition, under steady state condition means the VN Vout. So VN is 0 for a long time. You keep it like that. What is the resistance value? You can see, or otherwise you can put it to VN is equal to 1 for a long time and see how many whether both the transistors are on and off. So we know that from theory of the CMOS inverters under steady state condition. Okay, under steady state condition and without changing the input voltage from 0 to 1 or 1 to 0, we keep 0 for a long time, for a long duration, 1 for a long duration. Okay, so under steady state condition, both the transistors can never both transistors can never on at any input voltage, at any input voltage. So that means logic 0 we apply or logic 1 we apply. Okay, therefore it is not possible, therefore it is not possible to find out on resistance for CMOS devices. But we can individually calculate what is the resistance offered by what is the resistance offered by this PMOS, what is the resistance offered by NMOS also. So let us consider what is the individual resistance offered by the CMOS inverter? Okay. So by the by, what is the dimensions of this devices? This is a 1:1. This is also 1:1. This is also 1:1. So both the transistors have the same dimensions. So which means that it follows the 2 lambda by 2 lambda. This also follows the 2 lambda by 2 lambda. Okay. So it's not like a depletion mode type of transistor. So this is called RP. This is called RN. Okay. So therefore, what is the resistance offered by RP? This is Z simply into RS. So what is its value? Z is 1. Is multiplied with sheet resistance of the PMOS transistor. Sheet resistance PMOS. Let me write like this, more specific. Okay. So what about RN? It is Z is multiplied with RSN, NMOS transistor. So its value, what is this value? Again, 1 into RSN. So what is the value of this one? 1 is multiplied with, as we have seen, 10 to the power 4. Whatever the PMOS transistor, it is 1 into 2.5 times of NMOS transistor. That's what we have to consider from the table. So that's what we can see here. So in this diagram, you can see here. Sorry, in this table, it is a 2.5. So consider 5 micron technology. Assume, don't forget to write, assume 5 micron technology. Okay, so its value becomes 10 to the power of 10 kilo ohm per squared. This one, this value becomes, what is its value? This is 25. This is 25 kilo ohm per square. That is called RP. So therefore, individually, we are able to calculate the resistance of the transistor, but on distance is not possible to calculate. That's it. So this is the topic of the today's. We talked about the what do you mean by sheet resistance and how do we calculate the on resistance or a particular resistance of the circuit. Okay, we stop it here today. We will see the capacitance calculations tomorrow, and the day after tomorrow we talk about how do we calculate the delay of the circuit based on these two basic concepts like capacitance and resistance. By multiplying these two, RC delay will be there. How much of RC delay can be calculated for a particular circuit? We will see that one in the next class. We stop it here today. We'll see the remaining in the next class.